SwayamPrabha. Digital India. Educated India.
Hi, welcome back. So we're looking at the three-dimensional law of the wall, right, in the last class, and we said that we're looking for an effective velocity that correlates the 3D velocity profile into the 2D form, and the suggestion by several researchers for this V, there were like 5 of them, right, and then we understood kind of what the meaning of that is and so on and so forth like this. Now the point is, so then does this work, or do they do the experiments on that, or what is it? Okay, so let's go and just look at that. So this is the output. So the three-dimensional law of the wall by various hypotheses. Now this the one on the left hand side A, right, this is for small cross flow, right, this is for small cross flow, meaning W by V infinity, as you can see, is small, right. This W by V star is that's small, okay, and this one is large. This one here, for large cross flow, as you can see, this one is a large cross flow. This is W by V cross, okay, and all the references are given here. So you can see that pretty much when for smaller cross flow, all the methods seem to collapse into the same curve, so they don't make much of a difference, okay. But when the cross flow is large, then we seem to have a different all these methods. See, so this one is where we consider V as U sec beta. This is the arc length. This one? Okay, this is the Q cos gamma, and this is the V is equal to U, right. So that's where this becomes different. Okay, so that's that, and I think let's go ahead. So I wanted to just show this plot here. Okay, so now what we were going to do is start with the finite difference method, which was proposed by Nash back in 1969. Yeah, so let us see what we're talking about here. Okay, so this is 3D finite difference method. Okay, so this is a finite difference method which was proposed by Nash in 1969, right. So we use Cartesian coordinates, interesting, and we neglect viscous stresses. Okay, use Cartesian coordinates and neglect viscous stresses. Okay, I think it's time now to kind of relook as how we looked at the turbulent boundary layer, right. So the turbulent boundary layer, we there were several layers. There's a viscous sublayer, and the dissipation layer. So these were layers that we looked at. Okay, so when we say neglect viscous stresses, so I guess we're going to neglect that little distance or that little height of the boundary layer which is close to the wall in order to do that. Let's see how we will do that. Okay, this is nice to say, but when we're trying to formulate this problem, so how do we get to do that? So we are looking at a 3D turbulent boundary layer. So there's a 3D bit which complicates it, and then the next complication comes from the turbulence. So so we have been looking at several ways in which we could solve this problem, and we came up with the integral theories, and that's what we just discussed. Several methods. So this is again CFD, finite difference method. So so I thought we should look at this as well, how the 3D picture will develop. Okay, and what challenges do we have? Now then the basic equations become so. This is the continuity. Okay. Okay. Right, so we don't have viscous stresses, so therefore, the kinematic viscosity coefficient is not looking up. Okay, that's the U mean component. Then okay. Okay, and right, so these are the x direction, z direction, and y direction momentum equations, and we also have the turbulent energy equation, so which is this one. Okay, so okay. So this is the turbulent energy equation. Okay. Now the total shear stress is analogous to the 2D method. So the method of Nash basically in here, the total shear stress right is analogous to the 2D method, right. That is total is equal to okay. So essentially tau xy and tau zy, right? Right. This is about 15% of the. This is about 15% of the square of the velocity. Okay. Now we'll just look at something here. Okay. So in this here, we will look at this picture. So now what happens is in terms of the total shear, okay, in terms of the total shear, okay. Now same functions right and gy as fig in literature. So, I am going to show you that. Okay. So, this basically, now if I do that, so let us just go there and I am going to look at this, right. So, what you see here is the empirical dissipation, which is L, and diffusion is G functions for the turbulent energy differential method of Bradshaw and Ferris. Okay. So, L is essentially empirically is the dissipation and G is diffusion. So, if you see this axis is y by delta, okay. This axis 0 to 0.1 is L by is basically for the dissipation, L by delta, and on the right hand side is 0 to 40, which is the G, right, which is the diffusion G, and this is fitted from flat plate. So, well, this is fitted from flat plate data. Okay. So, this one is the L by this plot is basically from L by delta, and it is interesting to see that, okay, y by delta. So, y by delta is equal to 1 basically means that we are near the edge of the boundary layer, right. So, which is here, edge of the boundary layer, right. If that is so, then what do you have? So, G, so this is your L, L is your dissipation, okay. You have a little bit of a dissipation, and the diffusion is pretty high, as you can see, okay. And this is 0, this is at the wall. So, right. So, and then this is you can see that this is almost like a straight line, it's straight, it goes straight up, right, for about quarter of the boundary layer, height of the boundary layer or boundary layer thickness. It's actually almost linearly rising, and then it kind of becomes nonlinear, okay, the dissipation. So, we get this from here, okay. Now, so therefore, so right, so we use that for the energy equation, etc. Now, this results in 4 PDEs and 4 variables, okay, which are the velocity components and the shear stress, okay. And of course, we under the condition that of course known free stream conditions, so this is basically known free stream conditions, right. And again, since viscous, like I just started out saying that because viscous forces are neglected, that means that we are actually not going to go into the viscous sublayer of the turbulent boundary layer. We are considering a turbulent boundary layer, right. So, since right now, since viscous stresses, right, are neglected, so the equations are basically solved for y. So, equations are solved for y greater than 0. About 3% of the thickness. So, your y is going to be, so this is the, so about 3% of the boundary layer is the viscous sublayer, and we are not going to be considering that since viscous stresses have been neglected, right. But then we have to consider that. How do I mean I can't just neglect it, the viscous sublayer. So, then essentially we use the law of the wall to extrapolate data into the because we need the wall shear stress, then we will calculate the drag. Otherwise, what is the point of solving all these things, right? And that's, I mean, that is the major part when you are considering boundary layer, right? The reason you are studying boundary layer is, one of the primary reasons of studying boundary layer is to know what the drag will be like, right? So, then, the next thing you do is then use use law of the wall, right? How? Which is V is equal to under root this, right, to extrapolate to the wall and compute the surface shear stress. Okay. Well, sounds like a plan, but no. We'll again come up with a problem. So now, what's the new issue with that? Seems like nicely formulated and everything, but no, we do have a problem here. What do you think? Right, so we use the law of the wall, etc., to extrapolate the wall, extrapolate right to the wall, right, and then compute the shear stress. Now the point is, what is the direction of the shear stress? Which way, right? I need to know that. So the problem is how to ascertain the exact direction of the surface shear stress. Okay, so what do we do? Well, then what we will do here is, I think this is typically, typical CFD problems. We have issues about this kind of things at the boundaries. Okay, we discretize that, and if you're using, for example, a central difference formula, this is a finite difference problem, but say we're using a central difference formula, so then one of the points will fall outside the boundary, right? So that can happen on the left boundary or the right boundary. How do you do it? What do you do it? And so typically here, so we want to know what the direction of the surface shear stress is, and then but then I'm not going down to the solution. Going down to solution till the wall. I'm sort of cutting off about 3% of it, right? Then how do I do that? Well, we're basically then going to assume. What are we going to assume? Well, we're going to assume that the direction is the same as the nearest cell, right? So let's just say we assume viscous shear components right at the wall are identical in direction right to the turbulent shear components right calculated at the closest mesh point to the wall. Okay, so the viscous shear components, we take them to be identical to the direction of the turbulent shear components calculated at the closest mesh point to the wall, right. So that is what is assumed, right. Now, whether this will work or whether this actually is will make sense, well, that we'll have to see, right? That we'll have to see. We don't know that. Okay, so now then we get this relationship, and again I will look at a couple of plots, and that will give us some more idea. Okay, so in this, then what happens is, what we get is I just explained what beta was in last time or so. Okay, if you can think, is essentially okay, and that right. So, we are basically saying the viscous shear components of the wall are identical in direction to the turbulent shear components calculated at the closest mesh to the wall. Right. So, these are my these are the viscous shear stress components. So, the direction of these is the same as the turbulent shear components, which are calculated at the nearest mesh point. So, we're saying that the we're calling this tan beta. We're calling this the tan beta, which is the ratio of the viscous shear components. So, that's the direction. So, then the direction, right, is essentially the same as the turbulent shear components. Okay. Now, this relationship, right, now this relation is equivalent to the assumption. So, this essentially means, right, so this is equivalent to the assumption that so we assume a scalar eddy viscosity. So, this relationship is equivalent to the this basically means that what we are, this is the assumption. This basically means the assumption is that of a assumption of a scalar eddy viscosity, right. So, basically we are saying it is a scalar eddy viscosity. But when we do this, so essentially we land up with this trouble, and then we do this. So, this is essentially this, if we do this, when we say that the viscous shear components, the direction of that, the viscous shear components are at the wall. So, the slope of that, right, slope of that, or basically the direction of the viscous shear components, right, is the same as the turbulent shear components at the nearest mesh point. Right. So, this essentially means that we are assuming the eddy viscosity to be a scalar, right. It boils down to that, but the theory doesn't so we, although we said we are going to ignore the viscosity, basically what we are saying is that this relationship actually, because we are going to use that in this method, then it boils down to assuming that actually there is an eddy viscosity which is considered to be a scalar, right. But the value of it, however, is not calculated or proposed or theorized by these people. Okay. So, let us see. Let us look at some pictures. Okay. So, here so finite difference, this is the computations of so now the thing is, you do the finite difference computation, right. So, finite difference computation is done, right, and it is compared with the work of some experiments, right, in literature. So, this is the finite difference computations of Nash in 1969, okay, for the 3-dimensional flow experiment of Horning and Hubert of 1963. Okay. Okay. Now, so we have here, so this is the dashed lines. Okay. This is the dashed line here is for potential flow. Okay. So, the solid line here is for the span-wise pressure gradient. Okay. So, this is the cross flow profile. This is the cross flow profile. This is cross flow profile shown with the square markers. Okay. And this is the streamwise profile, which is showing with the showing with U. Okay. And so, as you can see, the curves A and B, right, A and B, potential flow and span-wise pressure gradient here, these are indistinguishable. Okay. So, this is the output of Nash's 3D experiment. I mean the 3D CFD studies that Nash did, and he compared that with his with experiments that were conducted 6 years before him. So, again, when we do the CFD, so just to sort of put back a little bit. So, when we do the CFD, again we make our analysis, and we again have to assume a few things, right, but we are able to come up with some solution which does not look too bad. Okay. And we are considering pretty much all of those equations, but having said that, I think it is also important to point out that we are not considering this equation like in full. Again, we are using the boundary layer theory observations here. So, although it is a 3-dimensional finite difference method, I would say it is not, it is kind of an adaptation of the finite difference method, because it is not just the finite difference method, but we do make considerations in terms of this being a boundary layer, and then according to Prandtl's theory for the 2D boundary layer, the way we have seen, right, taking one velocity component less than the other, and hence the pressure in this direction. So, it so turns out that the pressure gradient in the y direction is 0, right. So, we do that. Then we also make the assumption that we're going to ignore, or that the viscous stresses is going to be negligible, right. So, then with that comes to the issue that we do not consider the entire boundary layer thickness, where we solve these equations. So, we leave out about 3%, where viscous stresses will exist. So, we do not calculate that, but after with the solution, we then use the law of the wall to extrapolate and to figure out the wall shear stress, right. And while it seems like a good idea, then what happens to the but then we are not able to ascertain the direction, because of which then we assume that the direction of the viscous stresses is the same as the turbulent shear stresses at the nearest mesh point, right. So, again, I think this is an adaptation of, or a special case, or let us just say a modified version of a difference method, because it is not just a difference. We are not just taking the basic equations and solving them on the grid. We are not doing that. We are doing a lot of stuff with it, which is using a lot of theories here, and only then we are going to we are going to use the finite difference method or whatever else, right. So, in this case, finite difference method. Okay. So, that is that, right. Okay. Now, as we sort of inch closer to the end of this class, I am thinking more and more as to what sort of practical examples, or something that you can do with with your own hands and be a little more hands-on. So, I am trying to think on those lines as to so to show you, because it is difficult to sort of teach how to you can teach coding, but then as a part of this sort of a class to sort of discuss coding, I can't really, I do not think I can do that. And I think when you are part of this class and you sort of write codes as a part of the class, I think it aids really a lot in learning, especially for something like this. But that is not to happen. So, I think we will do with what is possible, right. So, I am trying to see how best to sort of make this a little more hands-on, without actually being. So, that is what we are doing right now. Okay. All right. So typically, so now like you saw, so whether it's so we did integral theories and now the finite difference method, but we are using a lot of assumptions and things like that, right? It's not like we just take the equation and solve it over the grid and then you get a solution. No, we're not doing that. Okay, so we are actually working with those basic equations and then working with those. Now, so through a 3D flow, right? So what we're going to do is look at turbulent flow parallel to a very cylinder. Right? Well, this is a special case of 3D axisymmetric flow. Okay. So, we will try to look at this a little bit. Okay. Now, the momentum integral equation has the same form as for steady laminar axisymmetric flow, and that is interesting, right. So, we can use the same like the steady laminar, steady axisymmetric flow, steady state axisymmetric flow for the laminar case. We are looking at turbulent flow here, okay. But the momentum integral equation has the same form, right, as for steady laminar axisymmetric flow. Okay. So, what is that? It is okay. Right, where R is, so these are terms that I have defined earlier. Okay. So, R is the local surface radius. Okay. So, R is the local surface radius. Okay. Right. So, we are basically looking at turbulent flow parallel to a very long cylinder. Okay. So, then let us consider the following classical problem. Okay. So, the classical problem is turbulent flow parallel to a very long cylinder of constant radius r is equal to a. So, this is essentially the classical problem, right, and radius constant radius a, right. Now, why would I do that? Now, then what exactly will be my objectives here, right? What will be my objectives? Okay. So, effect of transverse curvature on skin friction, right, or displacement thickness. Okay. So, objective is assess the effect of transverse curvature on skin friction, right, or displacement thickness. Now, in the viscous sublayer, right, of a thick axisymmetric turbulent, so let us write that down first. Okay. So, in the viscous sublayer of a thick axisymmetric turbulent boundary layer, okay, the momentum equation right is okay. Okay. So in the viscous sublayer, right, we are basically saying, yeah, so we kind of del r, okay. So r is the local surface, radius, okay, and so we take the gradient of the velocity in the r direction, right. So this is essentially giving us the shear stress, isn't it? So we write down, so shear stress basically, so del r of r into tau. So that's actually, so we just write r, and then tau we write as mu into del u mean del r, right. So that's the standard definition. Okay. So what we are essentially saying is that in the r direction, right, in the r direction, there is no variation of the shear stress, right. There is no variation of the shear stress, or actually let us just say total force, right. So the shear stress is say nu del u mean del r, okay. So that will be finite, but you multiply that by r. So this is essentially taking the shear stress and multiplying that by say r into 1, which is the thickness into the plane of the board. This is actually area. So shear stress into area is basically force. So force in that direction. So essentially this should give us the drag, right. When I say force in this direction where we have stress, the shear stress, so that's actually going to give us the drag. Okay. So so since we are considering the classical problem. So so the effect of transverse curvature on skin friction or displacement thickness, right. Very long cylinder. So essentially very long cylinder, which means that this height, the radius is small compared to the length. So that means when a boundary layer is forming, right. So we would like to know the effect of transverse curvature. So now you have a curvature, right. You have a boundary layer, you have a boundary layer, but then just think about it. I mean, why exactly are we taking this problem? So let's just say, okay, let me try it. Okay, I actually have a page here. Okay, so originally, just think about this. Okay, so originally you have a flat plate like this, and a boundary layer is forming over it. Okay, and now I'm saying that I have parallel to a very long cylinder. The boundary layer is forming to the parallel cylinder. How will I make this a cylinder? Well, just think about this. I'm going to just roll this up, right. it's almost rolling up the boundary layer, right. If you are going to roll up the boundary layer like that, that is it, right. So, parallel to a very long in a cylinder. So, you have a boundary layer which is forming like this, right, cylinder, you have flow moving like this, right, and then how will it look like as I go here. So, there is a certain curvature, right. So, this was the boundary layer, right, and you would go along x, right, and figure out various things, how is the displacement thickness as I go along x, right. What else, and what did we say? Yeah, and then how the shear stress is behaving, the tower wall, how will this look like? Now, the thing is, but then now you just see the same boundary layer is going to be, say, just like that, So, what was now lying flat, what was like flat on the ground, now actually has a curvature to it. So, how does this curvature affect, your skin friction as well as the displacement thickness? Does that have an effect on it? So, I think the basic, even if you think about a laminar, the flat plate boundary layer, if you just want to look at that, right. So, the basic thing we wanted to know was how much is the thickness as we go along x, right, the u velocity, what is the profile, and what is del u del y, near the wall, and how does that, the shear stress, and then how does that kind of behave. Right. So, in this case what is happening is, of course, this is a turbulent flow, it is not laminar flow, right. So, you have several layers in your boundary layer. So, you have, now we are talking about a viscous sublayer, right. On top of that, because of this whole cylinder thing, and this is a 3D thing, right. So, this is not something that you are going to be able to avoid. So, you need to talk about the fact that there is a curvature like this, and how is that affecting your boundary layer. Okay. So, I am going to do a little bit, and then kind of we will have to stop. Okay. All right. So, what do we do? So, integrating, we will integrate with inner law for the sublayer. Right. So, u is equal to 0 at r is equal to a. Yes. So, r is a means which is at the surface. So, that is your r, right. So, that is your r, and so velocity. So, that is the actually surface of the cylinder. So, obviously, there the boundary layer is the velocity is 0. Right. So, we will integrate this, that u mean is 0 at r is equal to a. So, inner law for the sublayer okay. Right, where this right. So, this is the wall friction velocity, right. So, this is so inner law for the sublayer. Now, this one, so this relationship, this one. So, this relationship, this is very different, right, from the 2D sublayer relationship, right, which is 2D equations for the sublayer, right. So, that is, so 2D that is essentially, okay, for such that if y by a is really so y by a is really much smaller than 1. So, then here, so then what happens, right, therefore, so I can just approximate that. Okay. And then, right, an analytic approximation valid for the entire boundary layer is obtained by replacing this y plus, right, by capital Y. So, let me write that. So, we are going to write that and then stop. Okay. So, and analytic approximation right valid for the entire boundary layer is obtained by replacing a y plus by y. And what is that y? Okay, which okay this right where typical values for B so you use either of these combinations or so I think so now we sort of again do all this analysis etc. So now finally we will write down the equations of the boundary layers along a cylinder. Okay. So I am going to stop right here okay, and then we will we'll finish this in tomorrow's class. Okay. So that's that. I'm going to just stop it here and finish this in the next class. Okay. So thank you.